Good morning, students. I hope that you can see my screen. Can you all see that?
Yes, madam.
Okay, so in last lecture, we were discussing about how to fit the multiple linear regression model when you have quantitative variables. So I have uploaded tutorial 1 and tutorial 2 as well. So as I told you, you can do both tutorials, and I will upload the answers of tutorial 1. So you can check your answers, but if you have any doubt, you can request a demonstrator to explain any question in tutorial 1 on Tuesday's session, and the full tutorial, all the questions of tutorial 2 will be discussed on Tuesday's session. So from that, I'll be taking marks. So you have to submit only tutorial 2 before Tuesday. Okay, so with that, now we know how to deal with quantitative variables and how to deal with qualitative variables when it comes to regression models. So in all the questions that we discussed so far, there was a response variable, and there were number of x variables. So the x variables are quantitative or qualitative. So whatever the number of x variables we had, what we did was we just took all the x variables and we took our response variable y and we fit our regression model. So in that case, we consider all the variables we have at hand. But when it comes to real life situations, when we have so many variables and when we want to fit a regression model, in most of the cases, what we have to do is we have to select what are the most suitable variables that we can use in order to fit a regression model. So that is known as the variable selection. Now, what happens in this variable selection? Now, let's say you have a variable response variable y, and you have p number of x variables, x1, x2, x3, up to, let's say, xp. So if you take all these variables and then if you fit the regression model, so that is you have p plus 1 number of parameters. You have beta naught, beta 1, beta 2, up to beta p. So if you just select from this p number of x variables, if you just select a subset, let's say you are going to select q number of x variables. So that is you have q plus 1 number of parameters. You have beta naught, beta 1, beta 2, up to beta q. Q plus 1 number of parameters you will be having. So in that case, what will happen if you just check the variability of the estimators? Now, for an example, let's say in the beginning you have 10 number of x variables. So we are going to select only 3 x variables and come up with the model. So let's say when you are going to select these 3 x variables, in the full model also, we are going to include x1, and in the reduced model also, we are going to include x1. So if you just check the coefficient of this x1, that is beta 1, if you check the variance of the estimator of beta 1, that is variance of beta 1 hat, you will see the variance of the beta 1 hat in the reduced model is always a less value when you compare to the variance of the full model. So, and in the other case, when you take the variance of the predicted value, the variance of the full model is a high value when it compared to the reduced model. So in that case, when you have less number of variables, the variance of the parameters, variance of the predictor, we can minimize the variance. So we know when it comes to statistics, we always look for a less variance. then we can come up with good predictions. So that is what happens when you select variables. So in this case, I have included in the theory. Now see, if you have p number of variables, you will come up with p plus 1 estimates, beta naught, beta 1 up to beta p. But we are going to select only q number of variables. So in that case, you will have q plus 1 number of estimates, beta naught, beta 1 up to beta q. So if you take the same variable and if you take the estimated value of that variable, if you take xj in the full model, if you take the estimate as beta j star and if you take its variance, and in the reduced model, if you take the variance of beta j hat, you will see variance of beta j hat is less than variance of beta j star hat. So in the full model, you can see a high variance value. So it's same as the when you check the predicted value as well. When you check the predicted value in the full model, that is a high value than the, when it comes to the variance of the predicted value, you will see the variance of the predicted value in the full model that is less than the variance of the reduced model. So in that case, since we have less variance in these coefficients, we are going to come up with these selected variables. So what we are interested here is we are going to find out what are the most suitable variables in order to fit our regression. So when it comes to regression models, there are several reasons why we come up with regression models. So one reason that why we come up with regression model is when you have so many x variables and when you have a response variable, when we want to explain the variation of these response variable with the use of our x variables, we come up with regression analysis. In that case, we are going to, when you come up with a regression model, we are using that regression model to understand the variation of y. And when you look at the R square, we will see how much of the variation is explained by our x variables. So these things we can do when you fit a regression model. And the second reason why we are using these regression models is that is for estimation and prediction. So in that case, we want to find out a regression model with a minimum mean square error value that is suitable for prediction and estimation to predict the future values. And the other thing why we use the regression model is to control the variables. To control the variables means, now for an example, let's say we are going to fit a regression model between sales and advertising expenditure. So let's say we have a model sales equal to 2 plus 0.5 times advertising expenditure. So if this is the model that we have come up at the end, now we know when you increase the advertising expenditure by 1 unit, on average, sales will increase by 0.5. So in that case, if we, by looking at the coefficient, we know if you want to increase sales by this number of units, how can we control the advertising expenditure? So in such case, by fitting the regression model, we can control our variables as well. So what we have to do is now when it comes to a regression model, whether to talk about the variation of the response variable, whether if you use it for prediction or to control variables, we have to come up with the best regression model. So in that case, we need to select the best set of variables in order to fit the regression model. අපේ regression model එකට අපිට ගොඩාක් x variables තියෙනකොට අපි regression model එක use කරන්නේ forecasting වලට වෙන්න පුළුවන්, variables control කරන්න වෙන්න පුළුවන්, එමත් නැත්නම් y ගේ variability එක explain කරන්න වෙන්න පුළුවන්. මේ මොන purpose එකට අපි use කරත් හොඳම x variables ටික තෝරගෙන regression model එකක් fit කරන එක තමයි ideal case එක. So in that case, what we can do is, when it comes to real life situations, what we do, we fit several regression models with the use of same response variable and different x variables. And in that case, what we do is we can check for the residual mean square value. We can compare each model and we can select the model with the smallest residual mean square value. And also there's another one called the CP statistic. So the CP statistic is estimated by this equation. You can see we have to take the sum of square residual divided by the variance and then plus 2p minus n. So p is the number of parameters you have in your regression model. So that is, for an example, if you have 3 x variables, you have beta naught, beta 1, beta 2, and beta 3. So in that case, you have 4 parameters. P is equal to 4. So in this case, you have to check this CP statistic. If the CP statistic is close to P, that is, if the CP statistic is close to the number of parameters in your model, so that is, your model is a good fit. So what you can do is, when you have several models, we can check in which model we have the smallest value for the residual mean square. And also in which model we have a CP statistic which is close to P. So when you check both these criteria, we can select the best model for our prediction. So that's how we select. So in this case, when we want to come up with the best model with the best possible set of variables, there are different methods that we can use to select these best set of variables when you have so many. Now, especially when you'll be doing projects, you will understand now, especially when we are collecting data using a questionnaire. In a questionnaire, we put so many questions. So when you collect information using a questionnaire, when you put all those information to an Excel sheet, you have so many variables as X variables, and you have a response variable. So in that case, if you are planning to come up with the model, if you put all those X variables and your response variable and fit a regression, then the accuracy would be a low value. But in that case, what you can do is you can select one of these methods and you can select what are the best variables that you can include in your model, and then you can come up with the best model for the prediction purposes. And in this case, when it comes to variable selection, there are different methods that you can use. So the first method that you can use is known as the forward selection. Now in this method, what you do is, first we come up with the model which has only the constant term. So that is, when you fit the model, first you take y equal beta naught hat. I'll just write it as, let's say, y equals c. So this is the initial model. So this is the intercept. So first you fit a model only with the intercept, only with beta naught. And then what you can do is you can check the relationship, the correlation between each x value, each x variable and the response variable. And then we are going to select the best, the variable which has the best correlation value. For an example, let's say you have 4 x variables. Let's say you have x1, you have x2, you have x3, and you have x4. So the first thing if you are using the forward selection, you have to do is you have to check the correlation between these variables. So you have to select the correlation between x1 and y. You have to check the correlation between x2 and y. You have to check the correlation between x3 and y. And then you have to check the correlation between x4 and y. So in this case, let's say when you check these correlation values, just put in random values. Let's say this is 0.56. Let's say this is 0.61. Let's say this is 0.84. And let's say this value is 0.21. So when you check the correlation values, you can see here x3 is the variable which has the highest correlation with your response variable. So what we do here, we select x3 and then we fit our model. So for the model, we take a y equal the intercept and beta 3 times. We can take x3 variable and fit our model. So then after fitting this model, you can check whether this variable is significant, and then we can check the R squared value. And then what we do is, after including this variable, if it is significant, we keep that variable and then we select the next variable with the highest correlation value. So in this case, that is 0.61. So we include that in the model and then we check for the significance of the variables, and we can check the R squared value. We can check the residual mean square value and CP statistic. Likewise, we add one variable at a time and check for the significance, and then we come up with the best model. So the drawback of this model is, now when we add a new variable to the system, sometimes a variable that we have been added before will become non-significant, right? It will become insignificant when we add. For an example, now let's say when you add x3, it is significant, so you keep that variable and then you are going to select x2 and then you are going to add x2 to the model. So when you fit the model with x2, you will, when you check for the R squared, residual mean square, CP statistic, and when you check the significance, you will see x3 variable is not significant when you add x2 to the model. So that is a drawback. So actually this is happening when you have the multico-linearity among the variables. So we have to come up with possible solutions. But here one of the drawbacks of this forward selection is this. That is, sometimes when we add a variable at the beginning that is significant, but when we add another variable in the middle, some variables that we have been added in the beginning, they will become insignificant. So that is one of the disadvantage. And another method that you can use to select the variables, which is known as the backward selection method. So when it comes to backward selection, what you have to do is we fit the full model with all set of variables. Now in this case, if you take the same example, here we have 4x variables. So we take y equal, we'll fit an intercept. We'll take beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus beta 4 times x4. We'll come up with this full model at the initial stage. We take all the variables and then we fit the full regression. And then what we do is we check what are the variables which are not significant, and then you can remove those variables and then you can fit the regression model again. So in this case, you can do, let's say, when we fit the full model, we can see x1 is not significant. So we can just remove x1 and we can come up with the new model without x1, and then we check for the significance of the variables. So likewise, we can just drop the variables starting with the full model. So in that case, we can also come up with the best model. So when it comes to backward selection, we have drawbacks as well. So sometimes the variables are dropped that would be significant when added to the final reduced model, because now in this case, now let's say when you look at the full model, sometimes in here we will see x1 is not significant. So we will remove x1 and then we will come up with the other variables, and when we check for the significance. But we never know when the best model, in the best model, sometimes x1 will be there with some other set of variables. So sometimes we may have dropped it in this in between steps when we are using the backward selection. So that is also a drawback. So because now when we use the backward selection and when we use the forward selection, we saw that we have drawbacks in both of these methods. So we can come up with a method which is in the middle of both. So that is known as the stepwise selection. So in the stepwise selection model, what we do is it's actually a mix of forward and backward. So in this case, what we do is we add variables at the same times. If there is a possibility to remove any variable which is not significant, we do remove the variables as well. Right, so in this case, this is also we can use in this one also we can use when we have when we want to select variables. So in that case, we fit a model. So we check for the significance of the variables. If a variable is not significant, we can remove that variable from the model. And also when we continue the process, if we feel like the removed variable will be good to add now, you can add that variable and see whether it's becoming significant or not. So in that case, we can actually, when it comes to real life situations, this stepwise selection method is the method that has been used in most cases. So we can actually use the stepwise stepwise selection model to select your variables. So what you have to remember is when it comes to variable selection, there are 3 types you can use. You can start with the intercept only model, and you can start adding variables and select the best set of variables, or you can start with the full model and then you can remove the variables one by one, and then you can come up with the good model, the best model. Or else what you can do here is you can use the stepwise selection model. In that case, you can what you have to do is you can consider the variable that you have recently dropped to be added in the next step if it is significant. So these 3 methods we can use. So I will show you how to use these methods in practically when we are dealing with the data set, but I'll be not explaining it today because we can do the practical. When we are doing the practical, I will show you how to deal with these 3 methods, how to, and especially when you are having the computer output, how to do this manually. I will show you. So that would be easy, especially when you are doing the exam also. When I give you the computer output, you should be able to perform the forward or backward or stepwise method in order to come up with the best model for variable selection. So we'll be talking about the practical session of that on Wednesday. For now, you have to just know that there are 3 methods that you can use in order to select the variables. Okay, do you have any questions from that part? Right, so if you have no questions, so in this stepwise regression, stepwise selection, what you have to do is like let's say when you add the model, let's say first you fit the full model and then you find x1 is not significant, so you drop that. And then you come up with the next model. And then in the next step, you find x3 is not significant, so you drop that. And then you fit the model. So in the next step, you can see let's say x4 is not significant. So you come up with the new model. So when it comes to that step, in order to add your models, because in stepwise, you have to consider about adding your models as well. So in that case, what you have to do is when you are considering the variables to add, I'll just write it here, then it will be clear. Now let's say in the initial model, you have your intercept, and then you have beta 1 x1, you have beta 2 x2, and you have beta 3 x3, and then you have beta 4 x4. Let's say this is your full model. So in the first step, if x1 is not significant, you can drop that, and then you fit the model with the other variables. So that is, you take your model, and without x1, you can just fit the model here like this. And in this step, let's say you recognize x3 is not significant. So what you can do is you can fit the model without x3. And here, when it comes to here, now you have to reconsider the variables that you have dropped to add back to the model. So in this case, from when we are coming from step 1 to step 2, we have dropped the variable x1. And when we are coming from step 2 to step 3, we have dropped the variable x3. So the recently dropped variable here is x3. So before that, we have dropped x1. So what you have to do is when you consider to add the variables, you have to accept the variable that you have recently dropped. You have to check the possibility of adding all the other variables. So in this case, you have to check, you have to add the variable x1 again to the model and check whether it's becoming significant. That is in the next step, what you have to do is you have to take these two variables, x2 and x4. At the same time, you have to check the possibility of adding x1 to the model. If it is significant, we have to keep that. We don't check the possibility of adding x3. So in this case, let's say x2 is not significant. So you can come up with x4 and x1. And in the next step, you can consider whether we are going to add x3 or not. So the recently added variable, we are not going to consider, recently removed variable, we are not going to consider that to add it for the system again, because if you add that to the system, you'll come up with the same model. So now in this case, to remove and to add variables, there should be 2 cutoff marks. So we will discuss that in the practical, how to use those cutoff marks and select and do this process when it comes to stepwise. In the forward and backward selection also, we will talk about that with the practical data set, how to conduct your forward selection and backward selection practical. Okay, with that, now when it comes to multiple regression model, one of the major problems that we see is, now when you have so many X variables and when you have a response variable, the ideal situation is we always want to have a good relationship with your X variables and the response variable. We need to have a good correlation between X and Y. But in some situations, in practically, there is a good relationship between your X variables as well. So for an example, if you check the relationship or the correlation between X1 and X2, let's say it's equal to 0.9. So in that case, there is a high correlation between your 2 X variables. So if you can see a high correlation between your explanatory variables, X variables, that is not good. So we call that situation as the multico-linearity. So in order to identify whether your model is suffering from multico-linearity, we can check this, we can use these techniques. One is, sometimes when you fit the model, there is a very good R-squared value, but only few parameters are significant. Let's say you have 5 parameters in your model: beta naught, beta 1, beta 2, beta 3, and beta 4. So you will see only, let's say only the intercept and beta 3 are significant, but you have a very high R-squared value, let's say 0.85. So in that case, it's not possible, because if you have a good R-square value, that means the variation of the response variable should be explained by your explanatory variables in a very clear way. There's a high variability of the response variable has been explained by your explanatory variable if your R-squared value is a very high value. But if you have only few significant variables, that is a sign for the multico-linearity. So you have to check for the multico-linearity if you see a high R-squared value and with small number of significant variables. And also, when you check for the pairwise correlation among the regressors, that is, when you check the correlation among X variables, if you can see a high correlation among your X variable, that is again a sign for multico-linearity. And also here, we calculate a statistic called variance inflation factor, which is known as VIF. So you can see VIF is calculated like this. So in that case, when you take this VIF value, so if the VIF value, normally we take as a general rule, if the VIF value is more than 4, that is not good. But if the VIF value is greater than 10, that is a sign for multico-linearity. And sometimes we'll come with a VIF value which is close to 1. So that is a sign that there is no multico-linearity, or there is no correlation among these variables, among the remaining variables of the system. So in that case, we can take, now for an example, the VIF value. When you calculate the VIF value is calculating for each variable in your system. So when you calculate the VIF value for X1, if it is close to 1, that is, there is no correlation between your X1 and the other X variables. And when you calculate your VIF value for X1, If it is greater than 10, that is, there is multicollinear. That is, your x variable is related with other x variables. So when you have multicollinearity, in most of the cases, what we do is we just drop that variable and see whether it's whether we can come up with good results when we drop that variable, whether we can get rid from multicollinearity, or else sometimes we use transformations. We'll be discussing about that. And also sometimes we can use multivariate statistical techniques, and there is something called ridge regression. We can use these remedies when you have multicollinearity to get rid from that. So with that, we are going to talk about heteroskedasticity. Now, when it comes to these models, so one of the major problems that we face when we are fitting the regression model, especially when it comes to the multiple linear regression, one is this multicollinearity. So we know now how to identify multicollinearity by looking at the R-squared value or by looking at the VIF value. How to identify this multicollinearity, and or else you can check the correlation between your explanatory variables. So another problem that you face when you are fitting this regression model is the non-constant variance. So even when it comes to the simple linear regression, and even in the multiple linear regression, we have the assumption that the errors are normally distributed with zero mean and constant variance. So in this case also, when you check for the constant variance assumption, so we discuss in the practical also, we can take the residual plot and observe. So in the residual plot, if all the residuals are nicely distributed in a constant band, if there is no pattern, we can conclude that the residuals are having a constant variance. But when it comes to the practical situations, in most of the cases, our residuals are not having a constant variance. So in that case, sometimes the residuals, we can see the residuals are having an increasing or decreasing pattern, and sometimes we can see some of the residual, we have so many positive residuals, and sometimes we can see so many negative residuals, and sometimes we can see, even though they are distributed in a constant band, we can see there are patterns. So if that is the case, now you can, if you look at these three graphs, you can see in the first graph, the residuals, the variance, that it's like increasing. It's having a cone shape. So in all these things, you can see there are patterns. They are not distributed randomly in a constant band. So in all these three situations, the residuals are not having a constant error. So what we can do is, if you just check what are the reasons for this non-constant error, which is known as heteroskedasticity among residuals. If the residuals are having a constant error, we call it as homoskedasticity. If the residuals are having, if the residuals are not having a constant error, we call it as heteroskedasticity. So in this case, if you just check why this heteroskedasticity is happening, why the residuals are not having a constant error, one possible reason is the natural factors. Now, for an example, if you take a variable such as salary, or the monthly income of a family, and the food consumption. So if you just take, let's say you're taking a Western province and you're going to collect the income of all the households in Western province. So in that case, you cannot see the same variation, because naturally the variation is, we cannot see the same variation when you take a variable like that. So the natural factors are there to see a non-constant variance. And sometimes another reason is error learning models. That is, for an example, let's say when people learn, they tend to do less number of errors. For an example, if there is a typist with the time, with the experience, and with the hours of typing in practice, so she will do less number of errors with her experience. So when she is having a lot of experience, she tends to do minimum number of errors. So with the experience, people learn and people tend to do small number of errors. So that is another reason. And another reason is data collection techniques are improving, and especially we have so many advanced data collection techniques, and because of these techniques there are only few errors are happening. So that is also another reason. And another one is the results of the presence of outliers. So if you have outliers in your model, sometimes if you do not remove these outliers, we can see the heteroskedasticity in your model. So that is also another reason for the heteroskedasticity. So in this case, in order to detect whether we have heteroskedasticity in the model, one is we can observe the residual plot. So we know how to obtain the residual plot using R. So by obtaining the residual plot, we can see whether the residuals are distributed in a constant band or not. Then we can say there is heteroskedasticity or there is homoskedasticity. So one thing is the graphical method. And apart from the graphical method, we have so many other tests in statistics to test the heteroskedasticity. So we have the Park test and we have the White's general heteroskedasticity test, and we have the Goldfeld-Kont test. So all these testing procedures we can use, but in most of the situations I have seen we are using the White's general heteroskedasticity test, but it's not a must. You can use any of the tests as you like. So in this case, if you take this Goldfeld-Kont test, in that case, if you are using this test, we need to come up with the hypothesis. So our null hypothesis H naught is whether error terms are having distributed with a constant variance. That is, error variance is homoskedastic. And then H1, our alternative hypothesis is error variance is heteroskedastic. That is, it's not having a constant variance. So in that case, for an example, let's say this is our initial model. So you have y beta 1, beta 2 times x and the error term. So if you are going to conduct this Goldfeld-Kont test in order to observe the heteroskedasticity, first thing you have to do is you have to take your data set and arrange all your x values in ascending order. Right? Take your data set, arrange all your x values in ascending order. And then what you have to do is, if you find any outliers, you can delete at this point. And then you take the remaining data set and you divide it into two parts. So let's say you have simple n number of observations, and let's say you are going to delete, let's say you have c number of outliers. So that is, you have n minus c number of data points now. So you divide it into two parts, then n minus c divide by 2. So the first set of observations you take into region 1, then the second set of observations you take to region 2, right? So we have the ascending order. We divide the data set exactly into two parts and take them into two regions. And then what you have to do is, we take the first set of data, we just fit least square regression model, the simplest model that we have discussed so far, and then we come up with its residual sum of square value, and then we fit a regression for the second set of data, and then again we come up with the residual sum of square value, And then we have to check for its degrees of freedom. So when it comes to degrees of freedom is equal to the observations we have n minus c divided by 2, and then minus k is the number of parameters you have in the model. So that is equal to the degrees of freedom. And in this case, we are going to calculate our test statistic. So the test statistic is you take the second model and take the residual sum of square divided by its degrees of freedom. And then you have to divide it by, you have to take the first model with its residual sum of square divided by its degrees of freedom. And then you have to check this with the table F value. So with these degrees of freedoms, you know how to check the table F value. If the calculated value is greater than the table F value, you can reject H naught. You are rejecting H naught means our data set is having heteroskedasticity. That is, the error variance is not constant. So with that, we can find out whether our errors are having a constant error variance or not. And another remedy that we can use is we can come up with weighted least square regression. So in the weighted least square regression, what you do is in the normal regression, this is our model. So here, when we use to estimate the parameters, what we did in least square method, we try to minimize the error as much as possible. So in this case, what we are going to do is we are going to give a weight to our error term as Wi, and we are trying to minimize this weighted error term as much as possible. So in that case, when you try to find out the equations for the parameters, what you can do is you can just partial differentiate these equations. And in that case, we will see the weight values they are inversely proportional to the variance. So but we know when it comes to the variance, we never know the true variance. So to find the Wi value, since we don't know about the variance, we can just substitute the sample variance here. And in that case, we can come up with the when you substitute the sample variance here, and when you take these two equations, when you partial differentiate these equations, you can find value for beta naught and beta 1 using x and y and w. So for x and y, you can substitute using the sample information, but for the w, you don't know. So for w, we are going to substitute 1 over sigma I squared. So sigma is also unknown. So because of that, we are going to take the variance, sample variance, and substitute it here to come up with the model parameters. So that is also one possible way to come up get rid from heteroskedasticity. And another thing that we can use is the transformation. So this is actually one of the most used methods when we have heteroskedasticity. Not only when you have heteroskedasticity, sometimes when you check for the assumptions, we will see even the normality assumption is also getting violated. So in that case also, we can use these transformations in order to come up with the good model. So in this case, sometimes when you use these transformations, when you observe the scatter plot, sometimes we will see there are non-linear patterns in the scatter plot. But then again, when we apply the transformations, you will see we can nicely come up with the linear pattern. And sometimes when we can get rid of heteroskedasticity, and then the accuracy of the model is also we can come up with a better accuracy of the model by applying the transformation, and also we can keep the normality assumption without getting that violated when we apply these transformations. So when it comes to transformations, there are different transformations that you can apply. But here, the most of the common transformation method that we are going to discuss is the Cox transformation. So when it comes to regression, this is one of the main transformation methods that we have been applied from a long time, and we are going to talk about this Cox transformation. So before talking about the Cox transformation, do you have any problems up to this point? If you have any problem, you can raise. Okay, so if you have no problem, what I'm going to do is I'm going to talk about in the next on Wednesday session, I'm going to do all the practicals. That is, I'm going to talk about how to conduct the stepwise regression and how to identify this heteroskedasticity and how to do these testings using R. So how to identify Multico-Linearity when it comes to practical situations. So those things we'll be discussing on Wednesday session. And after that, we'll talk about transformations. So if you have no problem, I'm going to end the session for today. Please submit your tutorial tutorial 2 before Tuesday, so I can mark it and give you I can take those marks. So please submit that. Okay, then if you have no questions, I'm going to wrap up the session for today. Thank you so much. We'll see you again on Wednesday. Tuesday, you'll be having the tutorial session. Thank you and have a nice day.
Thank you.